Okay, this is day 2 of electrochemistry, and I'm going to give this a shot here, and we might make a few mistakes along the way because I have about 10 different things that I'm going to try to show with this video. But what we're going to talk about today are overall galvanic cells, okay? Now, when we talk about electrochemistry, okay, a lot of what we talked about in the previous lesson was understanding and identifying oxidation and reduction. Okay, so hopefully now you have a good grasp of the fact that oxidation is when something loses electrons and reduction is when something gains an electron. Now, from that, we spawn off into 2 different types of electrochemical changes that can occur. So electrochemistry actually has 2 types of changes that we can produce. The first type of change is when we use electrical energy to actually produce a chemical change. So we add electricity, and when we add that electricity to some reactants, that's going to cause the change. And that's called electrolysis. The other type is when we use a chemical change to produce electricity. And that's what you're probably familiar with in terms of batteries, because that's what a battery does. Okay? In a battery, you are getting electricity from a chemical reaction that's occurring on the inside of a battery. Okay? Now, what we're actually going to do is we're going to start with this one. We will look at this one later, but we're going to look at this whole idea of batteries and making those first of all. Okay? Now, this type of cell is actually called a galvanic cell, or they're called voltaic cells. And again, it depends on the instructor, the textbook, who wrote the textbook, and all that. So galvanic cells or voltaic cells are kind of where we're going here. Now, one of the things that you have to understand is what is happening in a normal oxidation and reduction reaction. So let's say I have a normal reaction where I have solid zinc, and I'm going to add that to copper nitrate, copper 2 nitrate. Okay? Now, that copper 2 nitrate is aqueous. Now, normally when we do this reaction, this is a nice little single replacement reaction. And what happens is the zinc goes and kicks out the copper. So we get zinc nitrate. And then we get copper ions. And that copper ions are now our solid, and the zinc is now our aqueous substance. And what's happened is the electron transfer has occurred between the copper and the zinc. And we can write the 2 half reactions like we did yesterday or in the previous video for this. Zinc, which is a 0 charge here and a +2 charge there, zinc went from 0 to zinc +2, and the way it did that was oops, didn't mean to put an arrow there. The way it did that is it lost 2 electrons. And then that copper, which started out as a +2 charge, right up here, here's a +2 up there, he went to a 0 charge. Over here, he's a 0 charge right there. Well, how did copper do that? Well, copper gained 2 electrons, okay? So again, we've undergone oxidation and reduction, okay? And hopefully you can pick those out pretty easy now. Oxidation is loss of electrons, Leo. And reduction is gain of electrons, Ger. Leo, the line goes Ger. Okay, so we have our oxidation and reduction. And with this particular reaction, okay, these electrons transfer because this zinc is literally in contact with that copper. And I'm going to try to show that, and this is where things could go all wrong. Okay, so what I have here is a beaker of copper nitrate, okay? And here I have a piece of tin metal, okay? And I don't know if you can see that very well. Okay. Now, what I'm going to do, I'm trying to show you that there's nothing on the tin right now. Or, I'm sorry, I keep saying tin and I mean zinc. Okay, zinc metal. What I'm going to do is, that's a pretty good picture of it right there, is I'm going to put that right into the copper solution. And now, because that zinc is in direct contact with the copper, what's happening is that zinc is actually switching places with the copper. And when I pull this out, hopefully you can see, I'll try to get it there. See that dark half on the bottom? Okay, I don't know if you can see that. I keep moving it around on you. But see that dark path on our patch? There's a pretty good view of it. That's the copper that's been deposited onto the zinc metal. And the longer I leave it in there, okay, the more that's going to happen. Okay, so I have a little website here that I'm going to go to. Hopefully this works also, to also kind of show this. So here I have a whole bunch of different solutions, and I'm going to take this copper, or this zinc, and I'm going to put it into that copper solution, which is the exact reaction that we just did. And if we go micro scale, and we start looking at what's happening, these copper ions that were in solution are now depositing themselves onto the zinc metal. And you'll notice the zinc left the copper. So if I go back here, so you can kind of read this. Notice that in this reaction, the electrons are transferred directly from a zinc atom to a copper atom. Okay? And so as you go in there, those two are in contact with each other. And I don't know if you see that right over here on this top copper. The electrons were pulled out of the zinc and they were literally transferred. And that's what this equation is showing, is that the zinc loses 2 electrons to the copper, okay, and then the copper gains those 2 electrons, okay, and then the zinc goes into the solution. So again, taking a step back here to our video here, okay, that's what's going on right here, okay, and again, I'm sorry that I'm kind of moving all over the place, just trying to get this to see, but you can see that there's a direct contact here, and if I leave this in long enough, I know it looks black right now, but it will become that copper color eventually. And that's all happening again because we have an electron transfer. These electrons are transferring themselves to the copper, and the copper is becoming copper 2. And we can do that by direct contact. So, great. How does that translate to a reaction? Okay, now I'm going to come back to that. Well, what a galvanic cell is, in a galvanic cell, like a battery, we need to force that reaction to occur, but we want to, and this might be a bad term, we want to capture the electrons and use them to do something else, like light a flashlight, okay, or turn on our calculators, or turn on our cell phones. Okay, we want to harness those electrons and make them do some work for us, and we'll talk about the doing work part later. But we have galvanic cells, and what that does is it forces that electron transfer to occur through an external circuit. So what we're going to do is we're going to take those electrons and we're going to move them externally. We're still going to allow the reaction to happen, but we want to make the reaction happen externally. This produces a flow of electrons. Okay? And a flow of electrons is a current. Okay? And we'll talk about current later on as well. Okay? And we'll calculate different current flows and all that fun stuff. But that's what we need to do. Okay, so then the $50 question is, great, how do you make these electrons flow externally? Well, you got to remember what's happening, okay? So the zinc, oops, I did not want to put a charge on that zinc yet. The zinc needs to be able to give up its 2 electrons. And those 2 electrons need to be acquired by the copper. So that's kind of the flow if you think about what has to happen. The zinc has to lose the electrons and the copper has to gain the electrons. And the key to all of this is, sorry, I'm going to jump up and I'll come back. The key to all of this is what are called half cells. We need 2 half cells. Okay? Now, what's a half cell? Okay, well, each cell consists of a metal with its corresponding metal salt. Okay, so what you would start with, and I know this looks weird, but these 2 beakers here, those are going to be my half cells. Now, a half cell should sound familiar because what are these up here? What did we call those in the previous video? Half reactions, correct? Okay, well, we're going to make half cells. So in one beaker, okay, what we're going to do is we're going to fill that beaker with a metal salt. Okay, that's aqueous, by the way, and I don't know if I pointed that out. Okay, so what we're going to do is in that beaker, we're going to put some aqueous solution of zinc that will basically give us zinc ions. So when I put zinc nitrate into the solution, what's going to happen is I'm going to get a whole bunch of zinc nitrate ions that are really in that solution, or zinc ions, I mean. And what's nitrate going to be? In the end, he's a spectator. Okay? Now, the other part of that cell is we're going to put a metal in there. But we're going to put the same metal as the salt. So what we're going to do is we're going to stick a metal in here, but that is going to be a piece of zinc metal. Okay, so it's going to be a solid piece of zinc. So I'm going to go back to my diagram here. Okay, and I'm going to move this beaker out of the way a little bit. I'm going to move this beaker into play. Okay, now the beaker on the right is a solution of zinc nitrate. Okay, and what I'm going to do is I'm going to place into that zinc nitrate a piece of zinc metal. Okay, there. Believe it or not, that's 1 half cell. It's not doing much right now, but it's a half cell. Okay, and so by our definition of a half cell, it's a metal with its corresponding metal salt in aqueous solution. Okay, so now I need to do the other half cell. Great. Okay, so in the other half cell, what I want to do is I want to put some copper nitrate solution. So there's my salt. Okay, so I'm going to put some copper nitrate in there. Now, what does that really put in a solution? That really puts in my copper ions. So what I'm really getting out of the copper nitrate is my copper ions. And then I'm going to put in a solid piece of copper. Okay, so this copper is solid, and I guess I could have put that over here. This zinc is solid zinc. So let's go back to my picture here. So on the left, I still have my copper nitrate solution. Here, okay, you can see, hopefully that's a nice shiny piece of copper. There's my other half cell. Now, hopefully you would understand that. Is there any reason for copper nitrate to react with copper metal? Is there any reason for this beaker on the right to react with itself? Would copper replace copper is what I'm really asking. And hopefully you're answering no. The copper replacing copper has no reason to. Okay, they're already at the lowest energy state. Oops, went the wrong way. Sorry, knew that would happen. Okay, so now you say, well, great. You have these 2 half cells. They're not even in contact with each other. So how do you get them in contact with each other? Well, we have to get these electrons to flow externally. And because we're going to try to measure something here, we are going to connect this to what's usually called a voltmeter. And a voltmeter just measures voltage, and that's what we're going to put or talk about actually in our next VodCast is how to calculate this voltage. Right now we're just worrying about how to create a half cell. And so what we need to do is we need to take an electrode, and we need to take that electrode, which electrode is just a fancy name for wire, and we're going to connect that to the voltmeter, and that voltmeter is going to allow that to come over to the other side. We're going to connect that over to the other side. Okay, now, what does that look like in reality? Oops, again, went the wrong way. Okay, back to this. Okay, basically what we need to do is connect this with a wire. Now, for right now, I'm not getting a voltmeter out, okay? So what I'm going to do is I have a wire here, and we're just going to connect these two externally like this. Okay, so these two are now connected via that wire, and I knew that wasn't going to come out very well, but okay, I put some alligator clips on there, and they're connected. Okay, so now, so now we have this connected, but if you know anything about circuits, okay, what you should understand right now is we still have an open circuit, okay? And so at this point in time, we actually still don't have any electricity that's flowing, okay? We still don't have a reaction that's occurring because in a circuit like this, you need to have what's called a closed circuit. So the next thing we need to add to this is something called a salt bridge, okay? So we're going to add a salt bridge. And a salt bridge can be lots of different things, but in our case, what this salt bridge is, and I'm going to show you a picture of one, or I'm going to show it to you here. Which way do I go? Okay. This glass tube right here, I'm just going to set it there. Yep, figures. Doesn't want to sit. Okay. I'm going to rock back and forth really cool. That is a salt bridge. Okay, and what you do with that salt bridge is you are actually going to fill that salt bridge with a salt. So we're going to put some salt in there like KNO3. Okay, and we're going to fill it all the way up with KNO3. And what that KNO3 is going to do is that actually connects those two beakers. And now that I have those two beakers connected, the electrons can flow, okay? But now, how do the electrons flow? Well, you have to go back to the half reactions way up here. Zinc is going to be what loses the electrons, okay? So what's going to happen here is, out of this piece of zinc metal that I have right here, zinc is going to have electrons that are going to flow out of there, okay? Oops, I should do it this way, okay? So, out of this zinc, there's going to be an electron that flows out of there, and that electron is going to flow over here, okay? And that's going to happen a lot. These electrons are going to sit here, and they're going to flow over to the copper side. Guess what they just did? They flowed externally. Okay, now I have these two electron guys over here, and guess what copper is going to do? Okay, those two electrons are here. I have this copper ion, and I'm going to rewrite this so I get just one copper ion to play with. I have a copper 2 plus ion here, and that copper 2 plus ion is going to be attracted to those two electrons. And so I'm just going to get this outside here so we can see it. So when it picks up those two electrons, what's that copper going to do? Well, that copper is going to become Cu. Now, all of that's going to happen on this electrode right here. Okay, that's where that's going to happen, but that's happening all over the place. So these electrons then, okay, and they don't start back over here. These electrons just keep flowing through here. Flow, flow, flow. Make a whole bunch of little electrons. Oops, that's not going to work because I need to. Alright, what have I got here? Oh, I got 3 and 3. Yeah, these electrons are not going to flow on it like that. Okay, I knew that this was going to be an interesting little scenario as I started doing this. But those electrons are flowing through the voltmeter. And what's happening is this voltmeter will actually read or register a number. It will register what's called a voltage. And we're not going to worry about that today, but it's going to give us a power, and I don't want to say power. It's going to give us a voltage that we can read. And I don't want to get into voltage right now. So that's what's happening. And let me go to another website that I really like just to show you the same exact thing. So here's the same exact half cells that I just created. Okay? And I can put any metals I want in here. So I'm going to put in copper on this side, and I'm going to put copper nitrate solution. And then over on this side, I'm going to put zinc, and the solution I'm going to put is zinc nitrate. Okay, and then I'm going to turn this on. Okay, now as I turn this on, okay, what I just did is showing you what happens. And I guess I didn't show one part of it, but if you look over on the left, and I did this in backwards, you can see on the left side that the electrons are coming into that copper metal and the copper ions are flowing to the copper metal. Now I didn't talk about what's happening on the zinc side. The zinc side, if you see the zinc side, the zinc was losing the electrons, and look what happened all in here. And this is where I'm going to get in trouble. Okay? All those zinc ions that were previously attached with electrons are now no longer attached. And this is going to get me in trouble. Okay, maybe I can just close that now. Please close. Oh, something worked. And we can do this with different metals. So I could take silver metal and I could put that into a silver solution, and I could take copper and I could put that into a copper solution, and I would have two new half cells, and I could turn this on and we could watch what happens. Oh, I didn't clear out the zinc. But you can see now that the copper is actually losing electrons to the silver. So, in one case, zinc lost electrons to copper, but now copper is losing electrons to silver. Okay, so there's a lot that can go on with this. But these are galvanic cells. Okay? And so that is a galvanic cell. Now, one of the other things I didn't show then, or I guess I did show it, but the other point that we would want to make when we did this is, this right here then is the flow of electrons. Okay? So our flow of electrons is from the zinc to the copper. And then the other point that I didn't make very well is there is an oxidation cell and there is a reduction cell. Okay? This zinc, okay, from our half reaction up here is being oxidized. So this over here is the oxidation half cell. And that by default makes this the reduction half cell. Now, another term. Oxidation occurs at the anode. So this part of the cell is called the anode. Reduction occurs at the cathode. Now, one of the silly ways that I remember this is vowel, oxidation anode, consonant, reduction cathode. Okay, so oxidation is always at the anode, reduction is always at the cathode. So we can now make galvanic cells. So let's draw a galvanic cell for this particular reaction. Okay, so we're going to draw a galvanic cell for, apparently that plus right here should have been up there, sorry. So we're going to do Fe plus Ag yields Fe3 plus Ag. Notice, and I spoke about this in the first video, I believe, we don't really care about the nitrates or sulfates or whatever salt these are with, because that's not where the reaction is occurring. Those are just spectator ions. That's why we've all of a sudden changed this equation that it's still a single replacement reaction. We've just kind of changed it to ignore some things that we don't need. Now, one of the things that you want to do when you're drawing this galvanic cell is actually identify your half reactions first. I believe that's important. So if I'm going to identify what my half reactions are, I'm going to have Fe goes to Fe3 plus. And how did it do that? Well, it had to give up 3 electrons, right? And then the Ag, which was a plus, went to Ag, and it had to do that by gaining 1 electron. Now, in the previous video, we went ahead and we balanced this, but I really don't care about balancing at this point, because what I want is to find out which of these half cells is going to be losing the electrons, because that will tell me which one has to gain the electrons. And what that overall tells me is what the direction of flow is going to be. So I'm going to move these beakers down a little bit so I can make my half cells, okay, down here. And so what this tells me is, okay, I want a beaker, okay, that has some iron solution in it. So we'll call it iron nitrate. So I'll put an iron nitrate solution in there. And then I'm going to put a solid piece of iron. So there's 1 half cell. And then on the other side, I'm going to put a silver nitrate solution in it. And I'm going to put a solid piece of silver in that one. Okay, so there are my 2 half cells. Okay, those 2 half cells I need to connect externally. So we're going to put our voltmeter up here. And our voltmeter is really just a way to actually measure, okay, that we actually have voltage going on. And again, we'll talk about that. Okay, so we're going to have a voltmeter that's connected. And then the other important piece that we need is we need our salt bridge. So we're going to put a salt bridge in here. That salt bridge just needs to be filled with some particular salt. KNO3 works. Any salt you want to use will work. Okay? So now, again, okay, we now have a connection. We have a current that's going to flow. But what we need to figure out is what is going to be the flow of electrons. And that actually is why I like to write, oh, I knew this was going to happen. Why not? Okay. So, okay. So the reason why I write the half cells is because the half cell or the half reactions tell me that the iron is going to lose the electrons. So I know that out of this side, okay, I'm going to have electrons that are going to flow. Oh, it didn't allow me to do what I wanted to do. So I'm going to have electrons that flow out of that side, okay? So my electron flow we can pick out. And that's one of the things that I'll always ask you is to identify the flow of electrons, okay? And then the other thing you're going to have to be able to identify is the anode half cell and the cathode cell half cell. And again, that's why I like this, because you've already identified it. The Fe is losing electrons. Loss of electrons is oxidation. So this side is oxidation. Oxidation. Sorry. And therefore, it's the anode side. And over here, that silver is gaining of the electrons. And we see that right there. So this is the reduction side. And that would be the cathode. So that's how we draw half cells. Or excuse me, that's how we draw galvanic cells. Sorry, it's getting late. Now, one other thing that happens, and maybe I don't have it on here, okay? One other thing that we can do is we can have what's called a line notation. And what a line notation does is it shows you what the oxidation and reduction is going to be. So, and it's probably easiest just for me to actually show it. What you have is oxidation, half cell written first, and then you're going to put two parallel lines, and then you're going to put the reduction half cells. Okay? And now if you think about it, oxidation should always come first because oxidation is loss of electrons, and you have to lose something before something can gain it. So it kind of should make sense that oxidation is first. So what happens in this is this Fe goes to Fe3 plus. Okay, so that is our first half cell. And then what happens is the Ag plus ions pick up the electrons and become Ag. Okay, so that is the line notation. Okay, and you can see the line notation pretty much shows you what's happening. If I go back and I write the line notation for our zinc and copper reaction, okay, what you should remember is that the zinc lost the electrons, so that was the oxidation part of it, and then the copper 2 plus ions gained the electrons, so that was the copper half. Okay, so again, this side is the oxidation, that side is the reduction, and it's written as oxidation reduction. Okay, so that's just called line notation. Now, something else you might see in line notation, okay, and I'm just going to put it on these two even though it wouldn't be there. You might see another line with something like PT. And what that means is there was a platinum catalyst that was over on the silver side of this. And that really probably doesn't happen here. Okay, and it doesn't because we don't need a catalyst. But that, if you ever see that in a line notation, that's what it means. So over here, there might have needed to be a platinum catalyst to make this work. So you might see something out in front of that. Okay, and you actually might even see something behind that. Okay, and again, these reactions didn't need that, but just in case you ever see that in a line notation, that's what it means. So at this point in time, what I'd like you to do is work on the worksheet that I have attached with this so that you can get a good idea of how to draw some different oxidation and reductions.